Hello everyone, my name's Cooper Taylor, and today I'm going to be talking about drones. Drones have revolutionized many industries. These include agriculture, medical deliveries, and infrastructure inspections. In the recent California wildfires, drones were used to assess damage and aid in suppression efforts by the California Fire Department. Conventional drones fall into three major categories. First, multi-rotor drones. These drones are great at hovering, but they cannot cruise very far. Next is fixed-wing drones. These drones can cruise efficiently, but they cannot hover, so they need a runway to take off and land. Lastly, there's VTOL drones. This stands for vertical takeoff and landing. This has the utility of a multi-rotor drone with the efficiency of fixed-wing drones. However, these drones require separate propulsion systems, one for hover and one for forward flight. This increases weight and increases costs. These drones are also very hard to repair, upgrade, or change. So now I was very frustrated by these problems, so I set out to design my own VTOL drone to solve them. My drone includes two major aspects. First, an innovative tilt mechanism, which can be seen at the end over here. This tilt mechanism allows us to take off through hovering and rotate into forward flight, uh, eliminating unnecessary and redundant propulsion systems. Second is a modular fuselage over here. This modular fuselage allows the drone to be produced at a cost that's 5 times less expensive than the cheapest comparable VTOL drone. This drone was produced and designed completely by me from the ground up, and currently there are no peer-reviewed articles that document a constructed VTOL drone with this type of tilt mechanism or this type of modularity. Okay, now let's talk about the drone progression. Since this drone's initial design and building, March of 2024, it has evolved 5 major times. Each time, the drone's functionality. Oh, I apologize. I see network issues. Is everything okay?
Looks good.
Okay, I'm so sorry. Okay, with each redesign, the drone's functionality was tested through a series of flight tests. One can be seen in the top left, and its efficiency with each design, its weight balance, its aerodynamic performance was all improved till we reach our current version right here. And everything was built and assembled in my basement. So the drone works by transitioning through 3 major flight modes. Hover, which is first used for takeoff and landing, or also to stand still. Then we rotate into transition, by rotating our tilt mechanism, into transition to help gain speed. And then lastly, we move into forward flight, where we utilize the full efficiency of fixed-wing drones. Now onto the tilt mechanism. This is essential to this innovative VTOL design. This tilt mechanism is located at the end of each wingtip and enables the motors to pivot forward into hover and forward flight. Here we can see the tilt mechanism in hover, rotated forward 45 degrees for transition, and full tilt for forward flight. This allows us to use the same motors for vertical lift and cruise, reducing weight and redundancy. The tilt mechanism works by using a servo motor to rotate the mechanism and the motor about a stationary helical gear, and it is all enclosed in a 2-piece aerodynamic shell. Now onto the modular fuselage. The modular fuselage is made up of 3 main sections. The front section includes the camera, the middle section includes the battery and the airspeed sensor, while the rear section includes important electronics, such as the flight controller, which we'll talk about later, the electric speed controller, ESCs, the GPS, and the radios. It also includes the wing mounts, which can be seen here, and the tail mounts, which is in the back. The modular fuselage uses slots to make each piece quick and secure to assemble and disassemble. Everything's also constructed out of nylon PA12, which balances durability, cost, weight, and adaptability. Now onto the wings. The wings are made up of a 3-piece interlocking 3D printed sections for easy transport and repair, which can be seen over here. Inside of the wings, there's angled ribs, which are used to improve rigidity and minimize the weight by minimizing the amount of material that we use. At the end of each wing, ailerons are integrated. Ailerons are used for roll control and lift adjustment during forward flight. Let's use an example. Say we're in a hover, right? And now we want to go into forward flight. We want to generate as much lift as possible. So both of these ailerons would go up, the opposite of the position they're in right now. This would help us generate more lift and transition slower and safer. I used the NACA 4412 airfoil, NACA stands for National Advisory Committee for Aeronautics, for its high lift and because it's very predictable at many different speeds. Now onto our V-tail. Most tails that you will see on planes are formatted in a traditional T, but this V-tail was used because it allows us to reduce weight and drag compared to these traditional T-tails. A symmetrical NACA 009 airfoil was also used to ensure consistent performance in varying flight conditions. This tail, similar to the wings and fuselage, is also completely modular. The three main fins slot into an interlocking assembly base here. There's also a center fin which is used for stability. Two servo motors are located right here and right here to control the flaps and adjust pitch and yaw. Now onto my flight controller. When I set out to build this drone, there were no available options on the market for a flight controller that could stabilize this drone. So I had to build my own. After 19 different iterations, I built this flight controller design. And today I'll go through 5 major aspects of it. Starting with the left over here, we have the power supply. This connects to the battery and powers everything from the sensors to the microcontrollers to the motors. And it is optimized to minimize electromagnetic interference, or EMI, which can kill a PCB board like this. For example, this is very separated from the sensors and the flight controllers over here to prevent EMI. Next, our inertial measurement unit, which is right here. This is essential for stabilizing the drone, and it senses angular acceleration and angular velocity on 3 different axes. Next, we have our magnetometer. Our magnetometer is located right here in the middle of the drone. This is basically a 3-axis digital compass, and it really helps us out with navigation. Then, onto our fourth one, our barometer. Our barometer is basically a pressure sensor, and we measure the air pressure and compare it to standard sea level air pressure to use it as our altitude sensor. Lastly, we have our 2 microcontrollers. They are both ARM Cortex-M7 microcontrollers. One is used for telemetry, our logger right here, while the other is used for stabilization, our flight controller right here. Now onto our code. This coding was extremely difficult. Since there's no existing drone like mine on the market, there's no existing code that can stabilize it, so I had to write my own. I based my code on Dreamflight, which is written in C++, and it's an open source flight controller code, but I had to heavily customize it for my VTOL needs. I also used something called a PID controller. We can see the main equation right here. The PID controller is basically just a big feedback loop. It first calculates the error term, which is the difference between the current state and the desired state, where the drone is and where the drone wants to be. And then it predicts where the drone will go. And then it uses its different control surfaces to make the drone stable. This can include changing the motor speed or tilting the tilt mechanism back and forth. So basically, nothing is a direct input from the controller. Everything goes through the code and through the PID controller to make dozens and dozens of micro adjustments a second to stabilize the drone. Now, so we've built this whole drone. We've designed it, we've built it, and we've assembled it. But how do we even know that it will be aerodynamically efficient? That's why I employed computational fluid dynamic tools, or CFD. I employed a series of softwares, including XLFR5, ANSYS, and SOLIDWORKS, to evaluate the stall speed, lift, and drag of this drone. Using these softwares and the lift and drag equations seen over here, we were able to calculate that the stall angle for this drone is 14 degrees, with a stall speed of roughly 30 miles per hour. This is very comparable to fixed-wing drones. We were also able to calculate that the optimal cruising speed is roughly 45 miles per hour, and this was done by balancing lift and drag. Again, this is also very comparable to fixed-wing drones. I was also able to generate a series of pressure and velocity plots, which can be seen on the right-hand side here, which confirmed stable airflow and efficient aerodynamics. For example, let's take a look at the pressure distribution plot at 25 meters per second. High pressures in darker colors while low pressures in lighter colors. We can see low pressure right here above the wing.
2-minute warning?
Okay, we can see low pressure here above the wing, and that shows that we're generating stable lift. Now, onto future work. So, future work. I have already designed this three PCB system that works by incorporating a NVIDIA Jetson Nano AI chip into this drone. This will allow us to do fully autonomous and semi-autonomous missions. I will go through these three PCBs right now. First, we have the bottom PCB. This is the Jetson. This PCB houses a NVIDIA AI chip. Next, we have our middle PCB. This PCB printed circuit board houses all of our important electronics, such as our logger, our flight controller, all of our sensors. This also houses a 5G module for 5G connection and our precise GPS. Then on our top PCB printed circuit board, we have our power supply, our servo connectors, which are for our motors, and we have our two motor controllers for our propellers. We also have a battery connection up here. Using this NVIDIA Jetson Nano, we can do real-time object detection and collision avoidance using machine learning vision. One great thing about the modular fuselage that I designed is that to replace the old flight controller with this new flight controller, it's super simple. The old flight controller simply slides out and this new flight controller simply slides in. And since we're using different cameras for machine learning and vision detection and machine learning and object detection, we can simply remove with 4 screws our old camera and slide on our new camera. And yeah, that saves a bunch of money by having us not have to replace the whole drone with a new drone design to accommodate new features. Alrighty, now to the conclusion. To summarize, this drone includes a novel tilt mechanism that maximizes efficiency by using the same motors for hover and cruise. A modular fuselage also reduces costs and supports quick component swaps, whether for repairs or upgrades. Computational fluid dynamics and flight tests confirmed aerodynamic stability, smooth transition, and extended flight times compared to traditional multi-rotor drones.
That is
This
time, unfortunately.
Okay,
I'm sorry.
wonderful. And then I just have my references over here at the end.